Is this thing on, by the way? How do I know if it's on? It's on. Okay. He says it's on, so it's on. Okay. So we are going to talk about string theory, which is not quite the topic of this series of lectures, but I will get to why we are talking about string theory in a bit. So one thing famous about string theory is that string theory has extra dimensions. So string theory has 26 dimensions, but we just see 4. Where are the other 26 minus 4 of them? So if you have watched some PBS video or a Brian Greene video, you have seen him explaining this. The other 22 dimensions are curled up into small circles. If you look at a wire from far away, you only see a line. So that's what we see in the world. We only see 3 familiar space dimension and a time dimension. But if you zoom in, the wire becomes 2-dimensional. There's an extra curled up dimension. And that's the idea of compactification. We will take a dimension and compactify it into a circle. So the Brian Greene idea is basically you have from far away you have this, and you try to zoom in. What you see is something like a tube, which has an extra direction in which you can move it. Now let's try to do this in practice. For that, let's take, for example, the 25th spatial direction and claim that this is like a circle. So x25 plus 2 pi r is the same as x25. This is the idea of compactification. You are just identifying the 25th dimension modulo 2 pi r. And r is the radius of the compact dimension. Okay, let me do beta because that's what I have in my notes. Beta is the radius of the compact dimensions. All right. Now, the string action, the Polyakov version of the action for the 25th, for the 25th coordinate is 2 x25 x25. So if you don't know or have not seen Polyakov action, that's the Polyakov action. With some gauge fixing, etc. have been done. So the mu index takes 0 and 1. So this integral is over the 2-dimensional, what's called a world sheet. So this m, where we are taking the integral over, is called the world sheet. Now let's do something to simplify this. So let's define phi as x25 by beta. So that phi plus 2 pi is phi. So it's just a normalization.
So I have a question. So mu is 0 to 1, and these numbers are the same as the 25, right? So have we...
Mu and what?
Mu goes from 0 and 1, right? So so is the world sheet necessarily on this plane? We align the coordinates such that the world sheet is on this plane?
No, it's just that world sheet is 2-dimensional.
So I think he's confused because you're talking about the 25th dimension. So.
Okay. So let's do this then. You have x mu with x0, x25, and on the world sheet, the world sheet is another thing.
Yeah.
Not.
I think this is,
This is called the target space, and this is the world sheet.
yeah.
Are you still confused?
No, I like this notation more.
Okay. You just prefer this notation, that's it. Okay. So what we have done here is to just rescale this 25th dimensions radius so that the periodicity becomes somewhat simple. And also this is what you find in condensed matter literature. So the action is then to sigma b squared by 2 dA phi squared. Usually this constant in front of a kinetic term is redundant. You can just rescale phi to absorb that constant. But in this case, as we've just seen, rescaling changes the radius of the circle or the periodicity of the field. So beta is a genuine parameter that you cannot rescale away. Now, let me come in quickly why we are thinking about string compactification. The reason is this. This action is going to be, or this field, phi is going to be the dual to the fermion that we discussed last week. That will be coming in the next couple of lectures. For now, let's just focus on string theory. Any questions so far? No questions? Do you have any questions?
Yeah, all of it is a question. I don't know
Okay.
what's going on now.
Yeah, there's no way for you. Yeah.
So, is there some kind of metric on the world sheet or something?
Yes, that's also gauge fixed to flat.
It's gauge fixed to flat.
Mhm.
Okay.
That's a detail that I'm not going to care about.
So world sheets are always.
Yeah. Metric on world sheet is flat.
So world sheets always are they always isomorphic to R2 or like topological? Are they always topologically R2 or does that matter?
I will take it to be a torus lead.
Torus.
Yeah. So it's whatever you want in principle. A Riemann surface is fine. Yeah.
Well, I guess it has to have Euler characteristic 0, right?
I think you can, in perturbation theory, in string theory, you have to add up surfaces with different genus. But I think it still would have, the Euler characteristic changes with you putting holes in it, right? So
Yeah.
you have to add up all that, but
But then you
not
can't
going to
make
worry
it
about
flat.
it.
Then you can't make it flat everywhere,
Right. Yeah. Flat, let's say locally at least. Yeah. So now the claim that we are going to prove is this. So if I compute z of beta, which is, I assume everybody is familiar with path integrals. You said, okay, there is no way, even if you say, no, I cannot do anything.
You saw it
Yeah.
actually, right? Last
Yeah.
time, 2 seconds ago.
So,
It's okay, I'm pumped, it's fine.
yeah. So 2 sigma beta squared by 2 phi squared. So this partition function, which is a function of beta, is going to be equal to 1 by 2 pi beta. If you think about it, if we have a string moving in a target space which is a circle of radius beta, then it's completely equivalent to a string that's moving in a target space which is a circle and its radius is 1 by beta. So if I put the string in a target space with a small circle that's completely equivalent to this string in a moving in a circle whose radius is too big. Is that qualitative idea? So this is what we are going to prove. Any questions? Right, so this target space duality is called T-Duality. Now we know where the T is coming from. It's coming from target space. Is a statement of the duality clear? I think. So the idea is the string gets confused if it's moving in a small circle or a big circle. The point is, how it get confused, we will see then. Okay, now let's begin. First, let's think about the symmetries of this theory. One symmetry is obvious, which is the constant shift in phi do not change anything because the action only depends on the derivative of phi, and this corresponds to a current which we will call the shift current, and we'll define it to be that. So you can just do the Noether procedure with that symmetry and find out that that's the current. And you can check the mu J mu shift is beta square d square phi, and d square phi is 0 because of the equation of motion. So this current is conserved whenever equations of motion is satisfied. So we will say that this is conserved on shell. That's just another word for equation of motion is satisfied. But in 2 dimensions, we get another current for free. So free current, which we will call G mu of wind. We'll explain why wind soon, and this is defined to be 1 by 2 pi mu d mu phi. I'm using mu and nu, but remember that mu and nu are it's hard to switch notations now because I already thought about this in that way.
So that shift, is it this shift on the sigma coordinates? Or?
No, it's a phi that's shifting, right? The field itself, right? And it's easy to see why that is the current. Just make the shift space-time dependent, and so on. You know what to do. Yeah. So this current is conserved because of epsilon. Right, so if I try d mu wind, I will get 2 pi mu phi, so mu nu, and that's 0 because epsilon is antisymmetric and this is symmetric. Right.
Are we going to derive that, or?
No, you have it for free. If you want a slightly more, you want a slightly more geometric understanding, this is and this is 0 as the tautology, and that's exactly what this is. Right. So there is no derivation, that's just true. It's called the Bianchi identity. In
Bianchi identity in 2D.
yes, we'll make use of that also later. Yeah.
Wait, so actually, I want to go back. So that metric on the world sheet that I'm talking about, is that a Riemannian metric or is that the Lorentzian metric?
On the world sheet. Okay, I will keep it for Lorentzian, but later at stages I will,
Okay.
sleekly switch to Riemannian because I want to make certain qualitative arguments. But let's now keep this as Lorentzian.
Okay.
Right. I put an I there, right? Yeah. So. Okay, now to make things more interesting, let's take, okay, this is going to get confusing. Let's take the world sheet also to be, also to have interesting topological properties. So we will take the world sheet to be this, where R is for time is again a real line, and the space, the world sheet space, is a circle of radius R. So this is not the same circle as this, remember? So phi is a function of x and t. Phi itself is periodic, and now I'm saying that x is also, well, x is also periodic. Phi is also periodic, So there are two things that's periodic. Now, let's take an on-shell configuration. I'm trying to explain what this wind is. So let's take a static on-shell configuration. So on-shell configuration means equations of motion is satisfied. Static means that it doesn't depend on time. So the equation of motion is simply that. And this is easily solved to phi is plus 1. Right? Now let's try to evaluate the charge corresponding to this J wind. So we have Q wind to integral x from 0 to 2 pi r. That's the circle part. Is 0 wind. The charge is just charge density integrated over space. And that's equal to 1 by 2 pi integral 0 to 2 pi r x, and J0 is going to be epsilon 0 1 d1, right? If mu is 0, nu has to be 1 and blah blah blah, and d1 is nothing but dx. So this is dx phi. What we have is phi at 2 pi r minus phi at 0 by 2 pi. Right? So naively, it seems like Q wind is 0 because we have to identify the field at 2 pi r and 0. But due to this compactness identification or periodicity condition on phi, I can relax the boundary conditions. So naively, I would expect that this to be equal to 0 because I will identify field at the same point basically. But now I will relax it to this. Right? If phi at 2 pi r is phi of 0 plus 2 pi n, it's practically the same thing because of this identification. that clear?
No.
Right. So usually, 0 and 2 pi are the
I
same
agree
point.
that it should be 0.
Right.
I don't understand why you can say it's 2 pi n.
Because I can do that. Right? Because
0 and 2 pi are the same.
right.
Because of-
Because of this identification.
Oh, you just use a different term for 0.
Yeah. You
Okay.
can think of it like that. So what that gives me is this equal to n.
I have a question about this phi. It's ax plus b, but this is, doesn't seem to me like it respects this. Oh, I have to shift phi, not x. I apologize. Right.
You can shift x too. That's what we are doing right now, right?
Okay.
So what we end up is phi is nothing but n by r x plus b. So this phi is not single valued in that sense. But that's okay because the non-single valuedness is up to 2 pi. And phi is only defined modulo 2 pi. So
2 pi n over r.
2 pi n over r. No, if I put 2 pi r here, r's cancel, 2 pi n minus 0 is 2 pi n, right? So that's why.
But it would just be r, right? But r then have 2 pi r. If it's a circle, radius r. Okay.
Uh-huh.
I see.
Right. So n is how many times phi winds around the spatial circle. Right? If I have this is S1 R, which is the space in our problem, and what phi does is, it may wind around twice. So I will have n equal to 2, for example. And that's the reason why we called it the wind current, because the charge corresponding to the current counts how many times our field phi winds around space. And winding is quantized in the sense that winding is always an integer not because of quantum mechanics, because of topological reasons. Right. Is anything confusing so far? This is pretty confusing, so if something is confusing, please ask. Okay, I'll assume that it's not confusing, or I've lost you completely. All right, now let's try to derive that. So start with the partition function, and that's d phi exponential I 2 sigma e squared by 2 e mu phi squared. That's just the partition function. So I have to say that the coming steps are really confusing to me, and I don't think I've understood it properly. But I will try to explain whatever I've understood, and maybe after this I will understand it better. So this is the first argument. So we notice that phi do not appear in the action. Only d phi appears, right? Only d phi in the action. So why not integrate over d phi? After all, phi is not even single valued. D phi is single valued because the constant part is gone in d phi. So one might think that z beta. I don't know why one might think this way, but this is how this guy called Busher derived it. And I have no justification of, or no motivation of how he got the idea other than what I just said. So let's imagine that we are integrating over d phi, or let's call, let a u equal to d mu phi, then I will integrate over a mu exponential phi integral d2 sigma beta square by 2 a mu a mu. So I've put a question mark here because are we sure that this is equal to that? What do you guys think?
What is A? Okay.
A mu is just d mu.
Well, it can't be, right? It's probably equal up to some infinite constant.
Right, that's always the case with path integrals, but infinities, we'll just drop it. But let me make an analogy, then maybe it will be even more clear. So in electromagnetism, if you're trying to compute a path integral, then, okay, we try to avoid same notation. We'll integrate over vector potential e to the I s electromagnetism. What I'm trying to do is to say that, okay, why not integral d over electric field and magnetic field e to the I s e. Are these equal? Sure, that's there, yeah, which I'm not going to worry about. So the point is that the functional integration integrates over all possible functions for E and B, right? But not any function can be E and B. E and B must obey the following two conditions. This has to be 0. This has to be 0. These are the Bianchi identities for electromagnetism. Here, in other words, I want to ensure, wait a minute. I want to ensure that d mu phi epsilon mu is 0. When I write it like that, it seems like it's trivially true, but write it like this, a nu, and I'm choosing a nu to be any function while I'm doing this functional integration. I have to ensure that this is satisfied. That's the equivalent of making sure the Bianchi identity is satisfied, right? So if you forget about this and think of this A as an electromagnetic vector potential, what we are trying to ensure is that electromagnetic field is 0, right? This is nothing but the electromagnetic field. I'm sorry for you.
I appreciate it. It's also going to go on YouTube.
No, nobody's going to put it on YouTube, I think. So, I don't know. Okay. So this is not quite true. We have to ensure that Bianchi identity, which is what this is called, Bianchi identity. We have to ensure that Bianchi identity is true. So we could just put it in as a constraint, as I was talking to you earlier. So I'm going to try this z beta this integral be a, and I want to ensure that f is 0. So delta of f is a functional delta, infinite dimensional delta function, exponential I 2 sigma into square by 2 mu. Maybe that's better than what we had before. Yeah.
Before you switched from phi to A,
Uh-huh.
we wanted Bianchi identity to work on phi as well, right?
Right, but I'm only integrating over phi. Then phi is some function. Right.
I'm more asking, why didn't we need to ensure that that condition was fulfilled for the first one?
Right. So here I'm integrating over phi,
Yes.
and phi is any function.
But it cannot be.
Now if I take any function f,
It will be fulfilled in
and this is 0 because d square is 0 by virtue. This is, by the way,
that will be 0 without
this is,
what we take.
yeah, this is true for any function f, but this is not necessarily true for any function d nu f. That's the idea. Good question. Now let's go on. Oh man, this duster is bad.
Can use the third layer. There's a third layer of the blackboard.
Yeah, but I thought I would, keep everything up to the point and so on. Doesn't have to, but yeah, why not? So this delta function is slightly, well, we'll just make it a bit better by writing a delta function as another functional integral. It's just like delta x is dk to the ikx, something like that, factors of 2 pi, etc. Just like that, we will write delta f as integral over some other field, phi tilde, exponential minus I by 2 pi. All these 2 pi's will be convention, d2 sigma, phi tilde, epsilon mu, d mu, a. This is just like that. As with everything in functional integration, this is up to infinities and so on. Okay, so we have z beta equal to question mark d d phi tilde exponential I d sigma square by 2 d a mu minus I by 2 pi d sigma phi tilde mu d mu. Okay, now let's bring back the analogy that this A is like a vector potential. So what we have done is to set the electromagnetic field to 0 everywhere on the manifold, right? That's what this does. Does that not mean that the vector potential is 0 everywhere? Well, the answer is no. So why is that? So let's recall our lessons on the Aharonov-Bohm effect. So if we had some magnetic field over here, but outside here we have 0 magnetic field, that doesn't mean that the vector potential outside is 0. Right? I can make the vector potential 0 in a local neighborhood, but I cannot do it everywhere. And it comes up as the Aharonov-Bohm phase, that if I send a particle from here and make it complete a loop, then it picks up a phase. And the phase is Aharonov-Bohm phase. It's e to the I, the integral over this line element of the vector potential. In fact, we need this line integral over the vector potential to be not zero, because remember that our phi field had winding, and we don't want to lose the winding. So if I try to integrate over A, and let's try to choose a simple contour like the space direction. So that would be dx 0 to 2 pi r ax. And let's recall what A was from here. And ax is nothing but dx of phi. And this, we don't want it to be 0. We want it to be, where is it? We want it to be 2 pi times an integer, right? We want it to be right. So although we have set the electromagnetic field, or epsilon mu nu d mu a nu to 0, it doesn't mean that this is 0. Again, Aharonov-Bohm effect analogy. But we just not need this to be not 0. We actually need to impose more. We have to impose that this actually is 2 pi z. That has not been done there. We know that this is not 0, not necessarily 0, but we have to impose that it's actually 2 pi z. How do we do that? Any guesses? Are we confused?
Sorry, I got distracted.
Okay.
Now I'm just looking at review what was happening in the last 5 minutes.
Any other confusion other than distraction?
We could put in another
Delta
delta function,
function.
delta
I guess.
close loop integral minus n, and then some branch.
Right. So we will try to be slightly more clever, but in the end, get to the delta function. And that's what we are going to do now. Any other guesses? I don't know how these guys came up with it. It's just a paragraph in his paper. And I could not understand it properly, and I'm just trying to explain my version. So maybe, you'll figure it out now. So, idea. This idea is due to Verlinde and Rochek. What they did is to impose compactness on phi tilde as well. So phi tilde, which was just a scalar field, now I will say that phi tilde plus 2 pi beta tilde is phi tilde. Beta tilde is the radius of phi tilde. Okay, what's the point in doing that? So if phi tilde is compact itself, by the way, this periodicity is also called compact, if I did not define it earlier. If phi tilde is compact, what that means is that phi tilde also can wind around cycles in the world sheet. If the world sheet is like torus, phi tilde can also wind around in different cycles. Phi was compact and it could wind, so why not phi tilde?
I'm kind of lost. What is the connection between phi tilde and phi? Is there a connection between phi tilde and
No,
phi?
at this point, nothing. So phi tilde is just a Lagrange multiplier.
Yes.
Yeah.
So how the topos you would probably say it?
Yeah, that's coming. That's what I'm trying to say. So this is the idea
Yeah.
to make it compact as well. And if it's compact, it can wind around, of course. Then when we are doing a path integral over phi tilde, we have to, sum over all those winding sectors as well. Right? So let's imagine that phi tilde has a winding. So what that means is that if I take a closed contour integral over some curve gamma of d phi tilde, which I will just write d phi tilde. So if you don't understand this notation, just think of it as schematic. But it turns out that the schematic is actually the more precise notation. So just like here, integrating over a circle of d phi, we are integrating over a curve gamma of d phi tilde, and this has to be what? This has to be, 2 pi sum m gamma times beta tilde, just like here. The difference between these two, I can impose it to be 2 pi n beta tilde, because phi tilde is only defined modulo 2 pi beta tilde, and m gamma has to be an integer, right? And now comes a confusing thing that I have. The confusion I will explain later, but let me just go through this. For our particular example, I'm going to change the world sheet a little bit. I'm going to put the theory in finite temperature. What that means is to change time. Also, I'm going to now switch to Euclidean. Change time to be also a circle of radius 1 by temperature. So the world sheet now I change it to 1 by T cross R. So this is what you do to put the theory in finite temperature. So what that means is that the world sheet now is a torus with one radius. Radius along this way is, let's say, R, and the radius along this way is 1 by T. So I have 2 cycles around my world sheet. That means is that I have two types of windings. So I have 0 to 2 pi R dx dx phi tilde is 2 pi m along the x direction beta tilde. This sub x just means winding number in the x direction, and I have d tau 0 to 1 by t dt phi tilde is 2 pi m time beta tilde. These are the 2 windings I have for the finite temperature version of our string theory. All right. How does that help at all, as Diana was asking? So, as I said before, since phi tilde has winding sectors, we have to, what I mean by winding sectors is that, it can wind, that's it. It can have solutions like that. So the path integral, when we do the path integral over d phi tilde, we have to make sure that we also sum over these winding sectors or winding numbers. So in the path integral, we have the phi tilde. I'm just writing the phi tilde part, e to the I by 2 pi, and I'm going to just integrate by parts here, to sigma d mu phi tilde epsilon mu a mu, right? And this bit contains, okay, let me just write it like this, to sigma phi tilde mu a mu. This contains, this symbol just means this contains whatever follows. This contains, of course, dx phi tilde d tau a tau, right, where a is x independent and phi is tau independent. It has that, plus the other way around, d tau phi tilde dx ax. And we just wrote down what these bits are over here. So I have 2 pi mx beta tilde integral over a curve that's around time a plus 2 pi m tau beta tilde integral over curve that's space a. Now, this path integral also contains sum over all these winding numbers, right? Because winding number can be any integer. They have to take into account all possible windings. So in the path integral, I would have something like this. For example, m tau e to the that, e to the I by 2 pi, and the 2 pi's cancel, I m tau beta tilde integral O gamma x e. The path integral contains this. You see, this is a lot of hand waving, and that's because it's a partial understanding. So, and we know how to evaluate this, right? M element of z. This is given by 2 pi sum over k element of z. Okay, I have to look it up. Delta function of k gamma x minus 2 pi k by beta tilde. This is the standard formula. So remember what our goal was. We wanted to ensure this condition. But that's almost there. We just have to set beta tilde to be 1. And that's it. That will enforce the condition that A integrated over space-like curve gives you 2 pi k. Or in other words, a mathematician would say that, mathematician would call this a trivial holonomy. Just want to ensure that the holonomies are trivial. For that, all we have to do is to make the dual field compact with radius 1. Is that confusing? I mean, it's confusing, definitely. But any questions?
Sorry, can you repeat that last sentence?
Right. So to make the holonomy trivial, which means that integral over a cycle of gauge potential is 2 pi times an integer, all I have to do is to make the dual field phi tilde also compact with radius beta tilde equal to 1. That imposes this trivial holonomy condition, which means that It's called trivial because the particle do not pick up any phase. It's e to the I 2 pi n, which is 1.
Quick question about sum now. So when you say you sum up with m tau and mx, you sum the first term by mx and second term by m tau, and that's it. Like you sum them separately, right?
Yeah, so if some of them separates, you'll get an infinity and doesn't
Yeah,
matter.
that's what I'm saying. We get rid of those infinities,
Yeah.
right? Okay.
Modulo infinities. Everything about path integrals is true modulo infinities. So we have
You only do your path integration on phi tilde on those regions. Right?
no, all regions.
All
I'm just saying that this path integral, where is it? I lost it. I'm just saying that the path integral contains this as well. This is contained here. It's also there. I have to do other regions as well.
right.
But this region itself gives me the required condition.
Yeah, I'm saying on that region only you have that condition.
Right. All right, so we have worked a long way and we have discovered the fact that z beta, which was our original partition function we have up there in the first line, is equal to integral dA, integral d phi tilde, no question mark, exponential I to sigma beta square by 2 a mu minus or plus 2 pi to the d2 sigma d mu phi tilde epsilon a mu where phi tilde plus 2 pi is identified to phi tilde. If we enforce this, we did not lose winding, we did not lose Bianchi identities or anything. That's why no question mark. Now we do the classic trick of all time. We will switch the order of integration. We will first integrate over A. So, okay, this is easy. So I'm going to just skip. You can solve for the equation of motion of A and plug it back in because it's quadratic. The Gaussian approximation is exact. And, sorry, so you do integration over A, integration over phi tilde is left, and what you would get is 1 by 2, 1 by 2 pi beta square d mu phi tilde square. But of course, phi tilde is a dummy variable.
Before you go, sorry, I got a little lost before that. So we got that, again, it's after summation. Like, where we used what we did in the last 10 minutes to get from question mark to no question mark.
Right, so before, we did not knew this condition. We only knew that integral of A around a closed loop is not 0. That's all we knew.
Yes.
But we wanted to ensure that this is equal to 2 pi times an integer.
Yeah.
To ensure that, we have to put phi tilde to be a compact
Yes.
field. Once we do that, we have to be equal. We did not lose winding. This was the winding condition on phi, written in terms of A, because A is nothing but d phi. Is that clear?
So if I evaluate that integral for delta of f, but I do it only for compact phi, do I just get delta of f times
All the other delta functions. Yep. So that's the idea. So again, this is equal to this. It's simple. Just do the A integral. For that, solve for A and we plug it back in. And of course, phi is a dummy variable integrating over phi, which is of radius 1. But this coefficient has changed. That's all what happened. So we can read off from the first line of that this is equal to z of 1 by 2 pi beta. And that's the end of derivation for T-duality. Do you have any questions or?
So, why don't we see these large extra dimensions?
Yeah, I've been thinking about it. Yeah, I've been thinking about it, and I don't know if this T-duality just beats compactification to a circle. I'm not really sure. You know, people talk about compactifying to this Calabi-Yau manifolds, right? So, is this why people abandoned this idea? I have no idea. I think I have to ask Diana and the other Diana to get a right answer. So the answer is I'm not sure. Any other questions? So I have one more section, which is just one page, which is titled "What the hell is going on?" So if you want that, I can go through that. But before that, I will try to answer questions.
Can you give maybe one more shot at explaining? So this final line, you
Right.
sum over the winding numbers and then something.
Right. So we started with that, and then we claimed that only d phi appears. Why not integrate over d phi? But that is immediately, well, to really smart people, it's immediately not the same as that, because not all d phi counts as d phi, because you need to ensure d of that function is 0, which is the Bianchi identity. So Bianchi identity we put in as a delta function, that delta f is 0, and delta f we wrote it as an integral, then phi tilde is just a Lagrange multiplier that enforces f equal to 0. But of course, f equal to 0 do not mean that integration of the vector potential around the closed loop is 0. We remember Aharonov-Bohm effect and so on. So f equal to 0 f equal to 0 allows us to have this to be true, but that's not enough. I want it to be exactly equal to 2 pi z, because this integral is nothing but, if you substitute in expression in terms of phi, the winding. And the winding was that. I think I erased it. Now, how do I enforce this? For that Lagrange multiplier that we introduced, phi tilde, we take it to be compact. It's some radius. And we will tune this radius later. So if this Lagrange multiplier is compact, it can also wind. What that means is that it can have 2 winding numbers if my world sheet is like a torus. Then when I'm path integrating over phi tilde, I have to ensure that I'm integrating over these winding sectors as well, which means in this case the winding is determined by these integers, so I have to sum over these integers as well. So in the Lagrange multiplier term over there, I integrated by parts. You have something like this, where you have this, and it could contain phi independent of t and a independent of x, so I can separate the integrals and so on. And this is nothing but the winding condition for phi tilde, and this is this is the holonomy that we want to set to be trivial, that condition. So when we sum over mx or m tau, we have e to the I m tau beta tilde of the holonomy. And this sum is that. Just don't need any fancy stuff. This is just true. And So when we do this path integral over phi tilde, along with that delta f equal to 0, so along with that delta f, we also get this delta function multiplying that. So how do I ensure that this is equal to 2 pi k? I can just set beta tilde to 1. So then the partition function is completely equivalent to the original because we have ensured all conditions where phi tilde is there and so on.
Good question. Why did we introduce beta tilde?
Beta tilde?
Yeah, why didn't just set it up to the 1 to begin with?
Yeah, because
Then
I did not
we
know,
can-
right? So I did not know what if this was, 23 or something.
Okay, but
Well, 23
at
is
this
bad.
point, if we knew the results, it never was needed.
Yeah.
It could have been 1 to begin
Correct.
with, right?
So, if I did, in the beginning, remember I had x25
Yeah.
is plus 2 pi beta is x25. In that case, I would need x tilde 25 plus 2 pi 1 by beta or something.
Yeah.
So it's better to just put a beta tilde here and then tune it to 1 by beta or something. In this case, of course, but that's hindsight.
I'm just saying that in the end, it was like the natural potentiality. We could have set it up to 1 if we knew over, right?
Yeah. But that's a parameter I tuned to make sure that
Yeah.
holonomy. It turns out that I set up the problem in such a way that the tuning looks trivial. Any other question? Did that clear up?
Yeah.
It's still confusing, I think. I don't know, but so here's one confusion I have. If I don't take it to be at finite temperature, how do I ensure AX, the holonomy around X is trivial? Because it seems like to ensure the holonomy around one curve, I need another curve. That's what's happening. It's tau and X. So I don't know the answer. No book or no paper explains this.
Maybe that's
So
what we
this-
have been.
So this result is supposed to be for 0 temperature in the end, or? does
Yeah,
it
people
also
claim it-
hold for arbitrary finite temperature?
Now we just showed it for finite temperature, but people claim it for 0 temperature. That I don't understand, because in 0 temperature I do not have another cycle that helps me do the sum and get it. So I guess
Well, you
You
can
know,
just take the limit.
limit, yeah, exactly.
Maybe
That's what I was
that
thinking.
part kind of changes in a way that it still ends up being.
So, but, so let's say we're at finite temperature, we're looking at the finite temperature partition function, so it's already Euclidean or something.
Mhm.
Then is the claim that the duality, that the temperature on both sides of the equation.
It's the
of
same.
duality is the same. So
Yep.
temperature doesn't change, you just flip,
The radius of the compact boson.
okay.
So the world sheet features do not change. The target space feature changes. That's why it's a target space or T-duality. World sheet duality is a different thing, I think. Other questions?
So what is Calabi-Yau?
No idea. I think a torus is a Calabi-Yau manifold, for example. But I don't know the exact definition.
Well, you did this for X25. Do you just do this for the rest of them?
Yes, sure. Exactly. Any other question? Do you want me to stop, or do you want me to go through?
So the integration by parts, oh, is there more?
There is
More than
still a
just
little bit
one.
more, yeah. Yeah, the integration by parts is also a step that I'm really not sure because I have to pick up the boundary term, right?
Yeah.
Yeah.
Oh, since when we had no boundary term?
No, this is all about boundary.
Still, I don't
Yeah.
know. I
This
don't
is
remember-
topological, right? So all about boundary.
Yeah, it's all boundary term, but like, since when
Yeah.
was the last time we kept a boundary term in?
So one solution I found for that is to just start with this. Do not introduce this delta F and so on. Just start with that, and then kind of.
Yeah.
But this is slightly more intuitive in the sense that, yeah, people just start with that, by the way. Okay, so.
So if I, wait just a second. Okay, actually continue.
Yeah. So this is also going to be another hand wavy explanation. So if I take phi and its equation of motion is that, I can just separate it into the zero mode, which is the constant part of this wave equation, and the oscillatory part. Right? Oscillatory part is the standard wave equation solution, and the zero mode is just phi 0 is a constant plus at plus bx. Right? That trivially solves this equation. That's called the zero mode. And we know that B has to be m by r, where m element of Z is the winding. We did it previously where we looked at a static configuration where we did not have this. Now I can find the momentum from the action, and P is integral over the momentum density, which is integral dx 0 to 2 pi r. Momentum density, if you remember what the action was, is just beta square d tau phi. Okay, now I'm going to ignore this part for it's there, I'm just not going to write it, that's it. So this is equal to what? Beta square 2 pi r a. Do you want me to go through it very quickly?
Very quickly.
Yeah, so this is the equation of motion.
And then just splitting it into zero mode and the oscillatory modes. Oscillatory modes is the usual, a e to the I omega plus a dash, blah, blah, blah. And zero mode is just phi 0 plus at plus m by rx, because this trivially solves that equation.
Okay.
And m by r because we already found it in the past. We did not have the 8 tau part because we looked at a static configuration. And m is the winding, which is an integer. Now, I can find the momentum by integrating over the momentum density, which is that. And I'm going to not write the oscillatory part momentum density for now, because that's not relevant for this discussion.
And
this I can
just compute from this
to be that.
And since
phi,
phi, which is a spatial direction, is compact, the momentum canonical to that must be quantized. So P must be an integer. Oops, P equal to the integer. You can understand it from thinking about the wave function, which would have factors like that. And since phi plus 2 pi is phi itself, P times 2 pi times I e to the that should be 1, so P must be n. That's it. What that means is that this constant A is nothing but n by 2 pi r beta square. Now, we can also find energy, the Hamiltonian, in the ways that we know, integrating over the energy density. Ex, where is the expression? Half phi dot square beta square plus beta square prime square. You get it from that Lagrange. It's straightforward, or kinetic plus potential, just like in field theory. And this you can compute it to be pi by r. Just I'm only writing the zero mode part, of course. So E0 pi by r m square by 2 pi beta square plus beta square m square. Now can you see T-duality here? Remember, T-duality swapped beta with 1 by 2 pi beta. So if I swap beta with 1 by 2 pi beta, well, the zero mode energy doesn't seem to be invariant. However, if I swap beta with 1 by 2 pi beta and m with n, this remains invariant, right? So when I swap the radius and I swap winding for momentum, I get the same spectrum.
Can you just use like multiple of those?
Hmm?
Like swap n beta by n or 2 pi beta, right? Just doing
No, these are, part of the spectrum, right? So this is a swap of the parameter. This is some swap in the
yeah,
quantum numbers.
technically swapping the parameter times winding number.
Yeah, but if I say that x is a plus b, and I swap a with b, then that would be a trivial statement. That's what I'm trying to say. But this is a non-trivial statement in the end. If I say that I take this and call it that, and take this and call it this, that's like a trivial statement. But right. So the point is that if I take a circle and allow the string to move on it, the string has two quantum numbers, the zero mode. It has the momentum quantum number and the winding quantum number. So let's imagine that beta is really large. Then, this term is really large and this term is really small. So if I'm only interested in long range physics, this really heavy modes do not show up. Right? You need a lot of energy to see that. So if I'm in the infrared, the winding modes do not show up. And the physics is just the momentum modes. On the other hand, if I go to really small radiuses, then this is really heavy and do not show up in the IR physics, but the winding modes take over. So what's happening is that the string has two modes and they take turns to become relevant at small radius and big radius. That's kind of what's going on. Well, that's exactly what's going on, but if that's satisfying enough, it's up to you. Okay, more questions?
So when we prove this T-duality, we're just showing some property of the partition function, which we started out with a partition function that was Feynman-like with the Lorentzian metric, and then we switched to Euclidean sort of statistical mechanics-like. But
I could have just done all of it in Euclidean.
okay.
So,
But if we wanted like, I don't know, scattering amplitudes or something like that, we would put in sources and whatnot. Is that where the differences in these quantum numbers would show up? Or something like that?
So in string theory, you cannot put a source because that will violate conformal invariance. So this free action somehow gives you all of the scattering information as well by summing over all topologies of the world sheet. So at tree level, people sum over just a sphere with asymptotic states being brought back to finite points using conformal transformations. And then you have to go, to next order and so on. So if I'm doing, say, open strings, okay, if I'm doing open strings, something like this is first order, then something like that is, Feynman diagram with a branching, but at every point it's like a free string propagating and so on. So I don't know how that works though. It's just introductory chapter wisdom. I don't know the details.
So you only need to know the
Free action.
free partition function, or like the
Free action, but over all topologies. Well, you have to sum over all topologies to get the scattering amplitude to all loop orders. Any other question? Okay. Well, okay, this was a offbeat lecture in the sense that we're not going to use most of it. I'm just going to use the fact that there exists the phi tilde in the next lecture to derive bosonization duality. And then the last lecture we will do applications of that. Okay.